device, from cryptography and differential privacy to lighter weight obfuscation methods. On the left, you can see the flow. A user's private interactions generate local model updates, first the gradients, then parameters that may get sent to the server. Research has shown the updates aren't harmless. FedMF demonstrated that attackers can invert the gradients a client uploads to recover exactly which items the user interacted with. And more recently, Federated proved that even the parameters, the full model width and back, can be analyzed to infer a user's preferences. Together, these findings underscore a harsh reality. Sharing any form of model update risks leaking private data. As a result, when privacy is paramount, no client should participate in two consecutive training runs. Preventing an attacker from differencing updates and pinpointing a user's information. Here we focus on a different threat, which is the attribute inference. Attackers can collect the gradient updates you send and use them to get sensitive information about you, like the age, location, or interests, simply by analyzing patterns in those updates. And it gets worse. By inverting the parameter updates, they can actually reconstruct the lightened user vector and pull out personal attributes from that representation. To defend against these attacks, we need to go beyond hiding the raw user data. Applying additional privacy-preserving techniques like local differential privacy on the client before any upload, and combining it with more secure aggregation at the server can effectively mask both gradients and parameters, blocking attackers from inferring anything sensitive about the user profile. So I will first introduce the local differential privacy. With it, every device protects its update before sharing them. First, we clip the user's gradient so no single client can dominate the update. Then we add a bit of random noise, enough to mask any individual contribution, but still let the group signal shine through. Clients send only this noise, clipped updates to the server, which securely sums and averages them to improve the global model. Because the noise is added on device, LDP stops inference attacks in their tracks and keeps raw user data completely private. It's simple to implement scores well, and is by far the most popular way to protect user privacy in Federated today. While LDP adds noise on the client side, we can also log updates completely with cryptography. With HE, each client first logs its update in a cipher text and sends only that to the server. The server can then add up all the encrypted updates without ever unlocking them. Only the holder of the private key, which is often shared among clients, that can open the final sum and apply it to the global model. This means an honest but curious server never sees any individual user's update, offering very strong privacy. at the cost of extra computation and large messages. Early systems like FedMF and more recent graph-based methods such as FedGNN have shown that the HE can be made to work. That bit is the overhead. On this slide, we now introduce the secure multi-party computation. The key idea is quite simple. Instead of sending the full update to the server, the model split it into several random shares and send each share to different helper party. No single party ever sees the client's complete raw data. Those parties then work together, combining their shares to compute the aggregate update. Yet they never reconstruct anyone's private update. Only when a minimum number of shares come together can the original value be recovered. FedMMR applies the secret sharing trick to the inter-client convolution step. Each client divides its item hidden vectors into shares, exchange those shares with other clients, and then the MPC layer safely average all of them. The result is a rich, high-order interaction embedding that can capture information across users while keeping each person's data completely private. In many cases, we don't need a heavy crypto or formal DP to get a useful layer of privacy. Obfuscation and perturbation can go a long way. In FedMF, each client simply adds a little noise or a random mask to its greetings or model parameters before uploading. The slide shows one example. Here, each user generates a personalized mask vector, adds it to their true updates. Here, we denote it by ratings, and sends only the masked values. During aggregation, those masks cancel out, so the server still recovers the correct sum, yet it never sees any single user's unmasked raw data. This mask-based method is cheap to compute and saves bandwidth, but it's heuristic. There is no formal privacy bound, and a savvy attacker might eventually tease apart the noise. Still, for many applications, it strikes a good balance between efficiency and basic privacy protection. Another lightweight trick is to mix in the fake data or fake greetings with the real updates before sending anything to the server. In this pseudo-item or gradient approach, each client crafts synthetic interactions or gradient vectors that look plausible, and then blends them with the real ones. The server just sees a combined batch and can't tell which part is genuine. For example, Federated and Federated++ both use this tactic to hide true user feedback among decoys. So even if someone inspects the updates, they can't confidently pick out the real ratings or gradings. It's fast and easy. No heavy encryption or DP mess, but it's also heuristic. A clever attacker might eventually learn to spot the fakes. So it's often used together with stronger methods for better protection. In short, we have three main tools to protect the privacy in federated recommendations. First, differential privacy. Utilize each client and noise to their updates, giving a strong mass-backed guarantee, and even though too much noise can hurt recommendation quality. Second, cryptographic methods like homomorphic encryption or secured sharing fully hide individual updates, but they come with heavy compute and communication costs. Finally, obfuscation techniques. Things like random masks or fake gradients are lightweight and easy to add, so they offer only heuristic protection. Choosing the right mix of these methods comes down to balancing how much privacy you need against the extra work and the potential impact on model accuracy. So next, we come to the open challenges and future directions. So let's welcome Henshi.
Now we are moving on to open challenge. We'll look at the challenges that the researchers building these systems are trying to figure out right now. And we'll also check out the possible future trends that might change how this system develop. Now let's take a quick look at the challenge and solution of personalized federated recommender system, including 4 common settings and corresponding challenge and solutions. The first setting is static item identifiers methods. I will first introduce the background and challenge. For the background, in recommendation models, learning user and item representations is vital for personalized recommendations. An effective way to learn item representations is by using item ID features. Each item ID is assigned a unique embedding vector, enable the system to clearly differentiate among various items. This ID-based method is excellent at capturing an item's distinct identity, which has been a key part of many modern REXIS architectures. For the challenge, REXIS often deal with an enormous number of items. For example, an e-commerce platform like Amazon may have millions of items across various categories, from electronics and clothing to books and home goods. Similarly, a streaming service like Netflix could have tens of thousands of movies and other video content available for users to enjoy. In FedREXIS, these vast item catalogs present challenge in memory and communication. Client device with their limited memory and processing power cannot store the entire item embedding metric locally. Moreover, the federated optimization process, which repeatedly transfers the full set of model parameters between the server and clients, generates substantial communication overhead, hampering the efficiency of the FL workflow. We formulate the challenge as an optimization problem, which will guide the design of potential solutions. Specifically, we refine the optimization objective of personalized FedREXIS by introducing the memory loss and the communication loss for personalized item embeddings. Finally, formulated as a multi-objective optimization problem. Notably, both losses must adhere to the multi-objective balance constraint and remain with the predefined thresholds. To tackle memory and communication issues in FedREXIS, due to large item catalogs. A viable strategy is reducing the size of item embeddings stored on the clients. Instead of keeping the entire item embedding set, clients can store only embeddings of items they have interact with. This cuts local memory needs as the client-side item embedding set is much smaller than the full catalog. Furthermore, decomposing the item embedding metric into smaller sub-metrics on client devices is another effective solution. This not only conserves local memory, but also allows for the transfer of these decomposed submetrics during federated optimization, thus reducing the communication overhead. By using partial item retention and metric decomposition, Federated can efficiently handle extensive item inventories. It overcomes memory and communication bandwidth limitations on individual devices, enabling the system to scale and provide personalized recommendations despite the resource constraints of the distributed architecture. This is the solution diagram. The second setting is semantic-aware representation methods. Item attributes are crucial in REXs. Unlike relying only on item IDs, attribute information offers detailed item descriptions. This helps the system better grasp item traits and relationships, leading to more accurate recommendations. When dealing with cold start users or items, use item attributes can overcome the lack of interaction data in cold start scenarios. Also, item attributes can explain recommendation results, showing users that recommended items match their preference traits, boosts user understanding and trust in the recommendations. These advantages highlight the importance of using item attributes in Federated modeling. For the challenge, combining item attributes with multiple item embedding vectors allows for a detailed breakdown of item characteristics, offering a comprehensive item description. These diverse attributes provide a multifaceted view of item details and can aid in knowledge transfer among users. However, learning personalized attribute embeddings for each user might lead to overly specific item representations. This could impede the system's ability to collaboratively model user preference, thus harming recommendation performance. We formulate the challenge as an optimization problem, which will guide the design of potential solutions. We define the optimization objective by integrating a generality loss about personalized item embeddings, and the optimization objective ensures that Federated improves the generalization of attribute embeddings while minimizing recommendation loss, thus avoiding overly specific item representations. Among item attributes, those significantly affecting user preference often vary by user. Drawing from personalized federated learning concepts that learning partially personalized parameters, partially personalized attributes during